Hello and welcome to everybody on Cloud Fitness. So in today's video, we are going to learn one of the very important algorithm, which is the ridge regressions. And also, if you have not watched my previous videos, I do recommend watching them because without watching those videos, you are not going to understand anything in this particular video. So let's move ahead and see exactly what is ridge regression algorithm. But before moving on, I do recommend all of you to connect with me on LinkedIn, and I will leave the link in the description box as well. So when we talk about ridge regression algorithm, basically in my past video, right, I have already talked about overfitting and the underfitting model, right, and I have also explained how we can overcome this problem of overfitting and underfitting, right. Overfitting basically happens when your model performs well on your training set but it does not perform well on your test data set. Similarly, underfitting happens when your model doesn't perform well on your training data set and it may or may not perform well on your test data set. Now in this case, we use a technique called as regularization, which I also discussed in my previous video, right? And now this video is in continuation to that. We use something called as regularization. Now what exactly is that? Before moving on to the ridge, we should actually know what exactly is regularization. So when we talk about regularization, so this particular slide is from the linear regression video that I have already made. Now, if you look at over here, what is the main goal in the linear regression? In the linear regression, basically we have to find the best fit line. That is all we have to do. Y is equals to mx plus c, or yi hat equal to, theta 1 plus theta 2 of x, right? And theta 1 is nothing but the intercept, theta 2 is nothing but the coefficient of x. This is what we have actually learned, right? And then we also learned about the cost function. Now, cost function is basically nothing but the squared mean error, which is the difference between your predicted and your actual value. So your difference, now once you create your model, once you train your model, the difference between your actual and the predicted value should be as less as possible, and your cost function helps us to reduce it, right? So this is something that we have already learned from the linear regression. But now when you talk about regularization, what happens is, so our main goal is nothing but it is to find the best fit line, which is nothing plus y is equals to mx plus c. Now if you look at, in case you have multiple features, how is your line going to look like? How is your equation going to look like? Y is equals to c plus m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 plus m5 x5 and so on. Your coefficient into your x, into your value of x. X is nothing but your independent features, your input variable. Y is nothing but your output, right? So independent or your input features is nothing but x1, x2, x3, x4, x5. So all of this we have discussed. And y is nothing but the output, right? This is what your equation will look like. Now if the value of c is equals to 0, which means that your line is actually passing from your origin. Now in that case, what will happen is, so assume like if your c is 0 and your m1, m2, m3 has some values. Now let's say the value of y is 2.5 into x1, 30 into x2 and 50 into x3, right? Now these can be the value of y's. Now here what will happen is, now when we talked about this particular thing, regularization. In regularization, what is the main goal? Your main goal is to avoid any large variation in data. It is to avoid it is to minimize the value, the difference between your predicted and your actual outcome, right? Plus there is another thing, in our previous video we also discussed that that overfitting and underfitting can also happen if your model is complex. Now what does complex model mean? Now if you see this 2.5 into x1, 30 into x2, 50 into x3, now since these coefficients are high, 50, 30, 2.5, now since these coefficients are high, this increases lot of computational power on your model. So that is why we say that your model should be simple, right? It should not be too complex, because if it is too complex, it will cause the problem of overfitting, right? Now to reduce this part, right, now this equation can actually be reduced to something like your 2.5 can be reduced to 1.2, 30 can be reduced to 2.5, 50 can be reduced to 5. Now if something can be done like this plus 0.6, if you can add a variable, if you can add something to this particular equation in such a way that these coefficients can be reduced, right? Now in that case, what will happen is the computational power, right? Your model will become more performant, the computational power of your model will reduce, and at the same time, right, basically it will not need too much processing, and at the same time what will happen is that it will regularize your model in such a way that it will not have any kind of overfitting problem. Now this is what your regularization is all about. So when I say that, if you look at this particular diagram, right, you can actually see that, you know, let us assume this red line is nothing but the line that you have actually found out, right? This red line is nothing but the line which you have actually found out from your linear regression model, right? Y equals to mx plus c, this is the line. But now the moment you try to apply this logic, right, that I have explained just now, this regularization, your model will try to tilt this particular line in such a way that there is a small tilt, there is a very small tilt. It will try to tilt your model, and you can to tilt this particular line, and you can see this green line over here, right? Ridge regression tries to find a new regression line that does not fit the training data by introducing a small bias. So now basically when you're trying to train your model on the training data set, it will not 100% fit your training data, but it will be very close to your training data, so that later on when you try to put in your test data, it can pretty much fit your test data as well, right? So this is the whole idea over here. Now how does it does that tilting part, right? How does it do that? It does this by introducing a coefficient, by introducing this particular coefficient alpha and the summation of your beta square. Now this beta square, some people will call it as W, you know, there are different notations for it, but eventually it is called as penalty factor. Now what does it do? It tries to achieve the same thing that I described you over here by adding the penalty factor. Now this 0.6 what you see over here is nothing but it is the penalty factor that it tries to introduce. Now this penalty factor is nothing but, if you see over here, beta j square, this is nothing but sum of squares of coefficients. So now if I go back over here, now this alpha into beta square will be nothing but sum of square of these coefficients. This m1, m2, m3, m4, m5 is nothing but the coefficients. These are the coefficients that it tries to square and it tries to add over here, and then alpha is called as a hyperparameter. Alpha is called as hyperparameter. You try to introduce different values of alpha, in such a way that you try to achieve this particular equation, so that eventually what can happen is your regression line is a little bit tilt. It is not as steep as your actual line, which is trying to give you an overfitting model. So that is what your regression is all about. This alpha is nothing but this is called as your hyperparameter, and we actually try to introduce different values of alpha in order to get the best fit line. And the moment you do that, you will not see overfitting situation. Why you will not see? Because now your line has actually tilted, right? Now in this case, your model will be able to perform good on the training as well as the test data set. It will try to give low bias and the low variance situation over here. So this is what it is all about. This beta j square is nothing but the square of coefficients. This is nothing but the square of coefficient, and this alpha is nothing but it is called the hyperparameter. So I hope you understood the main reason why we have ridge regression. In our upcoming videos, we are going to discuss more on the ridge regression, how we can implement it, and also on the lasso regression and how lasso regression is different than ridge. So these are the few important things that you need to know, and do watch my previous videos so that these videos make much sense to you. You understand what this formula is all about. So thank you so much for being till here, and do remember to like, subscribe and share my channel. Thank you so much.